Hello and welcome to our part 2 of our chapter 8 video lecture. We are going to cover the skeletal muscles, structure, and function. And we'll be focusing on the fiber types, muscle actions, speed of muscle action and relaxation, force regulation in muscle, force velocity, and force power relationships. Starting with our muscle fiber types, we've got 3 of them that exist within our human skeletal muscle, and they are going to differ in these functional properties. So first, we've got our maximal specific force production. This property is basically going to tell us that the larger muscle fibers are going to produce more force than the smaller ones. And this is because they are going to contain more of our myofilaments, more actin, more myosin within our large muscles. So they are able to create more cross bridges, meaning that myosin head is binding to actin and pulling it in. Now, when we label it as specific force production, that is going to be the force production from the muscle divided by the size of the muscle fiber. Now, this is going to vary across the different muscle fiber types, so we're going to talk more about it a little bit later. And then the other property is going to be our speed of contraction. We will gain this property by measuring the maximal shortening velocity, which we call Vmax, and it's the highest speed at which the fiber can shorten. Now, what's going to really help with that? It's going to be the amount of myosin ATPase activity. If you remember, ATPase is going to help us degrade ATP into ADP and an organic phosphate. And the faster that we're able to do this, the faster we are able to cause that cross-bridge cycling so that we can contract. Then we've got our maximal power output, which is going to be our force that we talked about up here, times our shortening velocity, which is our Vmax. And a high force and a fast shortening velocity can produce a high power output. And the converse is going to be true as well. So if we have a muscle fiber that is going to have slow shortening velocities and a low force generating capacity, then we are not going to really have high power outputs. We'll have lower power outputs. Our fibers will also be different in how quickly they fatigue. So we'll see that our slow twitch muscle fibers will be fatigue resistant, whereas our fast twitch fibers will fatigue very quickly. And lastly, our muscle fiber efficiency. This is our muscle fiber's economy. How well is it at utilizing energy in performing work? The goal is to have less energy used up to perform a certain activity. So lower amounts of ATP will be used to generate a force. So how can we determine what the different muscle fiber types are? Well, we could opt to do a muscle biopsy where we are going to have a small piece of muscle removed, and you could see them doing that over here. This may not be representative of the entire body's muscle fibers though, because we are just taking it from one specific muscle, in this case the quadriceps femoris, which we know will represent different types of fibers because it is used within the lower limbs, helping us with our posture. So we will have maybe some more slow twitch muscle fibers here instead of fast twitch muscle fibers. And then we've got our immunohistochemical staining. In order to do this, we are going to try and identify the 3 different myosin isoforms that exist for each of the different fiber types. And so we use selective antibodies that are going to recognize the tag of each of these myosin proteins. So with that, we are then able to find this coloring given to each of the different muscle fiber types. So you can see that the type 2A fibers, which are going to be our fast oxidative fibers, are going to be green. And then the darkest blue here is going to be our type 2X fibers, which are going to be the fast glycolytic muscle fibers. And then we've got the lighter blue, which are representing our type 1 fibers. Those would be our slow twitch muscle fibers. And we've also done gel electrophoresis, where we are able to run the proteins through a piece of gel, which you don't see the whole gel over here. And essentially it is measuring the size of the proteins. And what we're able to see is that there were these different myosin isoforms that existed, and we can classify them based on the size of their proteins. Now let's take a look at these properties or characteristics based on the specific fiber types. You could see type 1 over here is our slow twitch muscle fiber, and type 2A and 2X are our fast twitch muscle fibers. 2A is going to be that fast oxidative type, whereas 2X, or sometimes it's called 2B, will be our fast glycolytic muscle fibers. So when we look at the number of mitochondria, we're going to see that it is lower within our glycolytic fast fibers, high and moderate within our fast oxidative, and high within our slow twitch muscle fibers, slow oxidative. And this makes sense because we know that our mitochondria are needed to create lots of ATP, in which we would use more of our slow twitch muscle fibers to go through the oxidative phosphorylation process to crank out lots of ATP. And with that, it's going to match the resistance that we have. Because we have so much ATP in our slow twitch muscle fibers, we are able to have resistance to fatigue, whereas in type 2X, when we're not making as much ATP to keep up, we are going to fatigue much more quickly. And so we see with our energy systems that the fast glycolytic will be using more anaerobic combinations, whereas our fast oxidative, it's a combination. So when oxygen is present, it is going to try and utilize that and use more of the aerobic processes, whereas if it's not as readily available, we are going to use more of the anaerobic processes. Now, what about our ATPase activity? We are going to see that our fast glycolytic muscle fibers are going to have the highest amount of ATPase activity because they are so great at getting the highest Vmax. So I'm going to pair this with what we see next over here, the speed at which we are able to shorten. And that's because these muscle fibers are known to generate the highest power output of all the muscle fiber types. So while this is great for generating power, it is going to be low efficiency because we are getting a greater energy expenditure per unit of work performed. So we're able to produce more power, but we're expending a ton of energy in order to do it. So we could see that the specific tension here is going to be high due to that force and power production. Whereas with our fast glycolytic fibers, we are still going to be high in both of these categories. Efficiency is going to be moderate, and then we have that high tension that can be produced. And we see the opposite taking place here with our slow twitch muscle fibers. We are going to be more efficient, have high efficiency, because we are going to be a little bit more conservative and utilize that energy in a more useful way in which we're getting more bang for our buck. In these next figures, we just have an illustration of what we talked about on that previous slide. So here you could see our 3 different muscle fiber types. Here's our slow twitch, our fast oxidative, and fast glycolytic, and we are measuring the maximal shortening velocity. We said that our fast glycolytic were going to be able to produce a very high amount of velocity, whereas our type 1 muscle fibers, they are going to have a lower myosin ATPase activity compared to the fast glycolytic fibers. So the type 1 fibers will have a slower maximal shortening velocity as a result. And here we are going to compare the force and power outputs. So here similar to our shortening velocity, our fast glycolytic is going to have a high amount of force, whereas the type 1 cannot produce as much force. And our power outputs, we see that we are really great at producing power within our fast glycolytic, whereas with our type 1, it is minimal. Now, there have been a ton of studies done to take a look at the muscle fiber type makeup within our skeletal muscles of our body. So we can take some of those studies and your book put them in this table to take a look at some of the elite athletes. Now, aside from the elite athletes, if we are an average sedentary man or woman, we are going to possess approximately 50% of slow fibers. But let's take a look at these elite athletes and their sports that they've been successful in. So if you are a long distance runner, you are going to have about 70 to 80% of slow twitch muscle fibers, whereas 20 to 30% are going to be made up of the fast twitch muscle fibers. Now, that doesn't necessarily mean that these people or these elite athletes that are successful in distance running are going to have that exact percentage. Someone can still be successful and have a higher amount or lower amount within this range. We see that there is a complex interaction between psychological, biochemical, neurological, cardiopulmonary, and biomechanical factors that all interplay with one another in order for an athlete to be successful. Now, if we do look at the opposite end, so we look at our track sprinters that are more of our power athletes, they are going to have 25 to 30% on average of the slow twitch muscle fibers and 70 to 75% of the fast twitch muscle fibers. So you could see quite a difference here when we are comparing our power athletes to our endurance athletes. And as we said, our non-athletes, sedentary, will be close to 50% for each of them. Now let's shift gears and talk about the types of muscle actions. You may remember talking about this in a past class. We do now use this term muscle action to describe the process of muscle force development. And we're going to describe these different muscle contractions that can take place. So we probably are used to using terms like isotonic contraction and isometric contraction. So the isotonic that you may have learned before is referring to our concentric and eccentric types of contractions. This is a dynamic type of exercise in which we're really having movement taking place. So here, if you look at figure 8.16, we can see the concentric contraction taking place within our biceps brachii here, where we are creating great force within our bicep in order to pull on our forearm and lift up that dumbbell here. So if we were to measure the overall length of this muscle, we would say that it would shorten or the muscle length would decrease. Whereas if we look at eccentric contraction here, when we are moving that dumbbell down, we are still producing force within the muscle, but the muscle is lengthening, it's becoming longer. And just a side note that this can result in high stress within the sarcomeres, those functional units within our muscle fibers. And this could be associated with injuring that muscle fiber, a loss of that muscle force generating capacity, and leads to muscle soreness due to inflammation and swelling within the muscle fiber. Now, you may think back to maybe when you were in our Wabash building and the elevators were so jam-packed, you decided to go from the 12th floor all the way down to the first and started going down the stairs. And that is a type of eccentric contraction that we're doing. And maybe the next day your thighs were very sore. Now let's talk about isometric types of contraction. That is more of a static type of exercise in which we're having that muscle contraction taking place and tension being created within the muscle, but there is no change within the length of the muscle. So if you were to hold a dumbbell or some other type of equipment and hold it in one place, let's say you were taking this dumbbell and just holding it at a 90-degree angle here, that would be isometric contraction. Or I always say if you are pushing up against a wall, trying to push that wall away, the wall is not going to go anywhere. Your muscle length is not going to change. So that is an isometric type of contraction. Now, when we get that muscle to contract, we want to talk about a single muscle twitch. That is that muscle contracting from one stimulus. So let's take a look at this figure over here on the right-hand side. When we get that stimulus from the motor neuron telling the muscle to contract or twitch, we are going to have this latent period, and this is because we are getting that action potential to move from the nerve to the sarcolemma and move down those T-tubules and cause depolarization of the muscle fiber. Then we are able to get those calcium molecules to bind to troponin, leaving the SR, right, to get to the troponin, and then causing that tropomyosin shift. And then we're able to form the cross bridges. And as we're forming those cross bridges, we are getting that tension to increase and contraction to take place. Now, once we get that contraction, we want the muscle to then relax. So we are going to reuptake that calcium back into the SR and get the myosin heads to detach from the actin filaments, and that is going to allow for the muscle to relax and come back to rest. Now, the speed of this shortening is going to be greater within those fast twitch muscle fibers. So if we go back and look at this graph over here, we can see that that shortening velocity is the highest in the fast glycolytic fibers. And we are able to have that sarcoplasmic reticulum release the calcium faster, and we have ATPase degrading the ATP much faster, so the myosin head can detach and let go and then reform that cross bridge very quickly. Now let's talk about force regulation in muscle. The more motor units that we have will allow for us to have a greater force, and also the faster those motor units act will help develop a greater force as well. And we have an ideal muscle length in order to produce force. We will see this on the next slide where we have a figure depicting this, because that muscle length is going to help give us increased cross bridge formation where the myosin heads are attaching to the actin filaments and allowing the sliding of actin toward that M line. Also, our firing rate of the motor neurons will play a role here. The frequency of that stimulation. You could see over here in this figure that we have simple twitches taking place. We get force produced in a muscle and it goes back down. These are our simple twitches. Then we could get summation to take place where we have a twitch, a contraction building force take place, but the muscle doesn't fully get to relax, and we get another stimulation that is going to cause another contraction of the muscle. And basically these contractions build within one another to add up, to summate. And eventually what we can have is no relaxation taking place, where we have a steady contraction or steady force being produced by the muscle, and that is called tetanus. And our contractile history of the muscle exercising can affect performance. So if we were to have a recent contractile history of this muscle, working out, doing some fatiguing exercises, then our subsequent muscle force production is going to decrease. We are not going to be able to perform well. But if we were to do some short periods of non-fatiguing contractions, most of you know this as a warm-up before starting your actual exercise, then we are able to see that there's an increase in muscle force production. And this is called a post-activation potentiation, or a PAP, in which we are having an increase in that muscle force production following that bout of non-fatiguing submaximal muscle contractions. So this figure here that I mentioned in the previous slide where we talked about muscle length and there being an ideal length for force generation, is depicted here. So we are seeing that when you have a muscle shortened already, so that we don't have much more space for the myosin heads to attach to actin and bring it in even further, we are not going to get a great contraction out of this muscle. Think about when you're doing a bicep curl. So if we were in this position already, are we going to be able to contract forcefully here? No, we're not. So we are going to want this second muscle length over here, where we have a nice amount of space and length for those myosin heads to bind to actin, which is in purple here, and bring in those Z discs closer and have that H zone disappear so that we get that optimal contraction taking place here. Notice how this says tension on the y-axis over here. So we are getting the max amount of tension here out of this mid length. Whereas if that muscle is elongated, notice how these myosin heads are barely making contact with actin here. So we aren't going to be able to produce as much tension and contraction here, and that's why we see that kind of falling off and decreased tension taking place here. We want optimal coverage of those myosin heads with the actin filaments to build the best or most optimal muscle length tension relationship. So we've talked a lot about muscle contraction, but what happens to our skeletal muscle if we are not doing any type of strength training or resistance training? As we age, we start to lose muscle, and that is called sarcopenia, where we have muscle loss due to aging. And about 10% of muscle mass is lost between the ages of 25 and 50 years old. I actually had a friend who really wanted to start getting serious about exercising and eating healthy, and so I recommended a scale to her, and she was like, oh, I actually already have that scale. I used to use it. And she went back into her app and it was able to measure muscle mass. And she saw that over a period of 10 years, she had lost 6 pounds of muscle because she was not working out. So that is quite a bit. And we see an additional 40% loss of muscle between the ages of 50 and 80 years. Aging is a result of the loss in those fast muscle fibers, and we gain slow twitch muscle fibers. And then, as we said, resistance training is important so that we put the stress on those muscle fibers and it can delay age-related muscle loss. Now, you do have a clinical application within your book, so there will be an assignment for you to read through this and complete a series of questions. Next, let's talk about muscle force velocity relationships. When we look at this figure on the right-hand side, we can see that this is our percentage of maximal force, 100 being the most, right? And then we have the velocity of movement. So this would be slower movements, this would be faster movements. And note that the green points here are our fast twitch muscle fibers, and the blue are our slow twitch muscle fibers. So when we look at this figure, there are two main points that we can see here. That at any absolute force, so we're looking along over here, exerted by a muscle, the speed of that movement is always going to be greater within our fast twitch muscle fibers. Note that at all of these forces, we're always going to see the green line further along having higher velocities of movement, right? And then our maximum velocity of shortening is going to be the greatest at the lowest force. So if we are down here at low force, we're always going to see that we have the greatest amount of velocity taking place. So the greatest speed of movement is generated at the lowest workloads. And this is true for both our slow and fast twitch muscle fibers. So why do we see these differences? If you remember, the amount of force that is being generated was determined by the amount of cross bridges that we created between actin and myosin. And when we have rapid shortening taking place, we are not able to make the best connections between our myosin and actin proteins in order to produce force. So as we decrease that velocity, we have more time for those myosin heads to connect to actin, and we are able to produce more force. Now we also see that our fast twitch muscle fibers are doing better at being able to produce more force at higher amounts of velocity. And this is because of two main things. We know that they have higher ATPase, so they're able to degrade that ATP into ADP and inorganic phosphate, allowing that myosin head to detach and reattach, forming more cross bridges. And then we also know that they are better at getting that calcium released upon neural stimulation. So having a shorter time period in which that calcium is released from the SR to go to the troponin is going to allow that contraction to take place much more quickly. And lastly, let's discuss the muscle force power relationship. When we look at this figure here, we can draw two main conclusions, and that is that at any given velocity, well, actually first let's orientate ourselves to this graph. We see here on the x-axis our velocity of movement as it's increasing, and here we see increasing power output. And the red here represent our fast twitch muscle fibers, and this teal is representing our slow twitch muscle fibers. So we are looking at any given velocity along in here. The peak power generation is always going to be greater within our fast twitch muscle fibers. We're always able to produce more power with the fast twitch muscle fibers. And this again is due to the same things we talked about in the last slide, where we have increased ATPase activity and we can more readily release that calcium to the out of the sarcoplasmic reticulum into the troponin. And then the other thing is that the peak power is going to increase with the velocity between 200 and 300 degrees per second. So within both muscle fiber types, we are seeing an increase within power as we get within this range, but then we start to see that there is a plateau of power output that takes place with this increasing movement of speed, and that muscular force is going to decrease with increasing speeds of movement. And we can kind of draw back to the previous slide here where we are seeing with the increasing velocity, we do start to lose some of that force. So that is in relation to this second point here. So that is it for our Chapter 8 lecture. We talked about in class the structure of skeletal muscle and the neuromuscular junction, how muscles contract, our exercise and muscle fatigue, the exercise-associated muscle cramps, the different fiber types that we had, our muscle actions, which were those isotonic and isometric contractions, the speed of muscle action and relaxation, and the force regulation within our muscle, and we discussed the relationships between force and velocity and force and power. As always, if you have any questions, feel free to reach out.